I will, in my talk, I will ask and try to ask and to give answers to the number of questions. And the first one, can complexity theory be applied to crystals and minerals in general? And in particular to zeolites. How can complexity of crystals and minerals be defined quantitatively? How it can be measured numerically? Then the next question is, does complexity of crystals has a physical sense? And which minerals and compounds are the most complex? And here zeolites come to the scene. And then how does complexity behave in geological systems, and especially with special attention of how they behave in zeolite paragenesis. And so the most simple question, for example, which zeolite is more complex? And here are pictures of zeolites from Moon Bay. This is Isle of Skye, so this is here in Scotland. And you can see there's beautiful crystals. And here you can see the tetrahedral frameworks in these structures without any extra framework cations. And so the natural question is to ask which zeolite out of these four is the most complex. And it is quite surprising that all these complexity theorists which are working in this field never looked at crystals from the viewpoint of their complexity. So and the reason is that they think that perfect crystals are quite simple objects from their point of view. So this is a paper written by Charles Bennett. He is one of the leading computer scientists in the world. And he says something like such intuitively simple objects as perfect crystals. So the complexity theorists, they consider crystals as simple. And, well, some crystals really are simple, so this is like halite. But if you look for zeolites, for example, this chortnerite, this is a zeolite mineral from the Eifel volcanic region in Germany. You can see that it has a very complex and intricate structure. So it consists from different types of polyhedral building units. So so we can definitely say that this structure is much more complex than this one. And can we invent some kind of parameter to characterize the complexity of structure in numerical terms? So it's always good to have a number which would characterize a particular parameter of the system. So then the first question, can complexity theory be applied to crystals and minerals? And how can complexity of crystals and minerals be defined quantitatively? And so I will give you some considerations which may appear as a bit simple, but they surely must be taken into account. So the first consideration is, for example, if we consider these two figures, so which one is more complex? I would say that this one, probably because it has 6 white vertices, whereas this one has only 3 white vertices. So this is the first consideration which we should take into account when we speak about complexity. This is what is called symbolic complexity, which is sensitive to size. And so the more parts the system has, the more complex it is. Then the next consideration is we consider, for example, these two graphs. So I would say that this graph is more complex because it has 3 different types of vertices, and this one has only 2. And this is a second consideration of complexity. This is what's called combinatorial complexity in complexity theory, which is sensitive to symmetry. So the lower the symmetry, the more complex the system is. So, and this is what our intuition usually tells us. So when the size of the system is increasing, then complexity is increasing. And when the symmetry is increasing, complexity is decreasing. So, but how to combine both combinatorial complexity and symbolic complexity in one single parameter? So, for example, just let us consider these six graphs, and we consider this graph is probably the simplest one, and this one is much more complex than this one. But can we really say which one of these two graphs is more complex? So we need a numerical measure. We need a number, and we can do this using the methods which were developed in complexity theory from using information theory. And the principle is very simple. The more information the object contains, the more complex it is. So we don't need any. So we need only a way how to express the information amount of a particular object in numbers. Better to have it in bits, for example, in binary digits. And for this, we can use this famous Shannon formula. And Claude Shannon was a kind of inventor of this information theory. And he published in 1948. He was working on transmission and transmission and communication of information. And so he proposed a formula to measure information amount of some particular message which has to be transmitted through some information channels. So this message may consist from n symbols, and if these n symbols can be subdivided into equivalence classes, and each of these equivalence classes contain this number of symbols, so then this is the formula which provides you the information amount of this message per one symbol. So here, Py is a probability of occurrence of particular symbol in this message. So this is, it's calculated very simple. So this, the calculation is very simple. So you take just the number of these symbols in a message and then subdivide it by the number of symbols in the whole message, the number of all symbols in the message. So for example, if you consider this message, so consisting from these symbols, so here it has 11 symbols, and then they belong to 3 classes, and then you calculate probabilities, just subdividing these numbers by this number, and then you apply Shannon formula to get the information amount per symbol. In this case, it is about 1.6 bits per symbol, and then the total information amount is about 17.3 bits per message. And how we can apply this idea, this Shannon formula, to spatial structures, so the structures which exist in space. So I mean the discrete structures which exist in space, because crystals are discrete structures which exist in three-dimensional space. So probably the first one who applied the Shannon information theory to describe information amount contained in some topological structures. So for example, in some graph, was Nicholas Rashevsky, and he was one of those scientists who left Russia after the Bolshevik Revolution, and he worked at the University of Chicago. And so he said we should consider graphs as messages, and vertices in the graphs consider as symbols, and then symbols belong to the same class if the vertices are symmetrically equivalent or topologically equivalent. So in this case, so for example, this graph contains from 4 symbols, and 3 symbols are identical, and 1 symbol is unique. So what we can calculate, now we can use Shannon formula to calculate 2 numbers. So the first number is information per vertex, and the second number is information per graph. So in this case, we have a very good numerical estimate of information which is contained in some particular graph. And so we can see here that this graph is more complex than this one because it has higher information amount per vertex and per message as well. And we can apply this idea in the same fashion as Rashevsky applied it to graphs. We can apply it to crystals, because crystals, and we can take a reduced unit cell and then consider its content, its atomic content, as a message, and then the atoms as symbols, and then consider symbols to be identical if atoms are equivalent in symmetrical in terms of symmetry. So so we can simply write information amount of some particular structure in terms of information amount of its unit cell, like here. So this is a number of atoms in the reduced unit cell. It's better to use a reduced unit cell, and this is a probability of occurrence of particular atom from some particular group. So this value is calculated also in a very simple fashion. So this is a multiplicity of crystallographic orbit. So I mean the number of atoms of particular crystallographic type in the reduced unit cell, and this is a number of atoms in the reduced unit cell. So if you consider this equation, so this part is sensitive to the size of the system, the size of the unit cell, and this one is sensitive to the symmetry. So this part reflects symbolic symmetry, symbolic complexity, and this part reflects combinatorial complexity. So in one single measure, one single number now have combination of both symbolic and combinatorial complexity. And you can calculate these complexity parameters very easily just by hand. And so, for example, this is information calculation of information content per unit cell for the zeolite AFI. This is idealized model of this zeolite. So this is a multiplicities of some particular atomic sites, and then you calculate this probability, and then you multiply it by binary logarithm of this probability, so you get the value. This is topological information per atom, and this is topological information per unit cell, expressed in bits. So now, for any crystal structure, you can just use this this procedure to calculate the information amount for any particular structure. So, and actually we did it for the whole inorganic crystal structures known so far using this software. This is program package for topological and crystal chemical calculations, which was created by Vladislav Blatov at Samara State University. So you can, it's free for download. So you can, here you can see the information measures. So you just upload your crystallographic file with atomic coordinates, and then you calculate, you get these numbers, these two information amount numbers. So, so for zeolites, we calculated information-based complexity parameters for all zeolites. And so when I submitted this paper to the micropost and the post material, so it was accepted within 2 weeks and with no comments. So it was really surprising for me that probably the reviewers thought it's much too esoteric. I don't know, but anyway, so now we have for any type of zeolite framework, we have numbers which reflect their complexity. And so, especially for example, for these minerals, now we can put in correspondence for any framework. For any mineral, we can put into correspondence two numbers. One is the number of bits per atom, and another number of bits per unit cell. So from the viewpoint of number of bits per atom, so the Thomsonite appears to be much more simple than the other zeolites. It's important to distinguish between structural and topological complexity. So the structural complexity, for example, this paulingite. This is a very rare and very complex zeolite. And so the structural information takes into account all atoms and real symmetry. And topological information reflects to the ideal symmetry and considers, in the case of zeolites, considers only so the tetrahedrally coordinated and oxygen atoms. So in this case, you can see structural information is always higher than the topological information. So here are the numbers. So the next question, what I would like to ask is: does complexity of crystals have a physical sense? It's an interesting question. And if we speak about complexity, we surely turn to the entropy. And entropy of crystalline solids consists of several different parts. So one is configurational entropy, another is vibrational entropy, and there are some entropy which is due to some other effects, for example, magnetic, or some chiral interactions. And so if we speak about configurations, so atomic configurations, then probably it's configurational entropy, which is the most important here. And configurational entropy is usually estimated using this famous Boltzmann equation. Here, this is a Boltzmann constant, and we multiplied by natural logarithm of W, and W is a number of microstates that realize a given macrostate. So, if, for example, crystal consists of n atoms, then the highest possible configurational entropy would be if we exchange, if all atoms belong to the same crystallographic site. So all atoms are equivalent. Then this W would be just the number of permutations of these atoms over the whole crystal. So this is n factorial, and using Stirling formula, we obtain this is a maximal configurational entropy for crystal consisting of from n atoms. But if, like in zeolites, we have crystal in which n atoms are partitioned into some k crystallographic sites, so they contain from n1 to nk atoms. So in this, so and in the total, so this is the total sum of all these n and y numbers. So the total number is equal to n. So, and then the number of microstates is equal to this equation. So, and you can easily see this. So, for example, if you have a crystal consisting from 4 atoms, and then if all 4 atoms are equivalent, then the number of possible permutations is 24. So this is 4 factorial. And if these 4 atoms are split into two crystallographic orbits, each consisting 2 atoms, then the number of possible permutations is equal to 4. So the difference is 6. So you have to. So it's really large difference. So and just using some simple mathematical procedures, we can calculate that this is a possible maximal configurational entropy, and this is configurational entropy in the case when all atoms are not equivalent. And here you can see that this here appears this Shannon information per atom. So actually, this information, which is estimated using the formula, which using this Shannon equation, has direct relation to configurational entropy. So the higher the information, the lower the entropy. And actually, you can go in further, and you can estimate how the one bit of information, how much energy it costs. So there is this idea of information to energy conversion, and there is a famous Landauer constant, which states that to erase one bit of information in general, you have to apply at least this amount of energy. So this is a minimal amount of energy which you should use to erase 1 bit of information. So the conclusion is that complexity expressed in the Shannon information has a physical nature and represents a negative contribution to thermodynamic entropy of a crystalline solid. And so the next question, which I would like to consider, is complexity of zeolites versus complexity of other minerals and inorganic compounds. And here you can see the distribution of 2,000 most complex inorganic structures according to their chemical identity. So about 60% of the most complex inorganic crystal structures are polyoxymetallites. Well, this is a huge cluster, so of course they will have a huge unit cells. They will have usually low symmetry. But you can see that the zeolites, they come number 4 if you rank all the structures according to their complexity. So zeolites are really one of the most complex inorganic structures known so far. If you consider 20 most complex minerals, which means crystalline solids which are produced by geological processes. So you can see here that out of these 20 minerals, 9 minerals, so these 9 minerals are either zeolites or some open framework aluminum silicates. So the most complex mineral known so far is actually paulingite. So this is a zeolite. So paulingite is the most complex mineral known so far. And then come some minerals which belong to this concrinite sodalite modular series. And indeed, the paulingite is very complex. So and this is some nodal or graphical representation of its topology, and it was actually recognized as the most complex mineral by Alan McKay, professor at the University of London, I think. And the most complex zeolite in general, so it's taken also into account synthetic compounds. This is this zeolite SSZ57, and it has about 20,000 bits per unit cell, and paulingite has about 7,000 bits per unit cell. So this the difference is about by the factor of 3. So the crystals produced by humans, they are much more complex than crystals which are produced by nature. So this is kind of classification of zeolites in terms of the complexity of their frameworks, and you can see that the most most of zeolites, they belong to this intermediate range of complexity from 100 to 500 bits per unit cell. The simplest zeolite is sodalite. The simplest topologically, from topological point of view, is sodalite. This graph shows distribution of frequency of occurrence of some particular complexity of zeolites. So this is bits per unit cell, and these are bits per atom. And this is a number of different topological frameworks. So the next question, which would be very interesting to ask, is how does complexity of zeolites behave with increasing temperature? So, and let us consider two cases. The first case where there is no dehydration, and another case where there is dehydration. So, in the case if there is no dehydration, so there is just a few examples in the literature, and I found, for example, this is a Weirachite. This is a mineral with analcime topology, and with increasing temperature, so at room temperature, it is monoclinic, E2/A space group, so its complexity parameters. It transforms at high temperature, transforms to tetragonal space group, and its complexity is decreasing. So its information amount per atom and per unit cell is decreasing. And another example is the leucite. This is again analcime topology, and it's tetragonal, and it transforms to cubic. And again, we see that the complexity is decreasing with increasing temperature. So complexity is decreasing, which means that the entropy is increasing with increasing temperature. And if we speak about dehydration, and one excellent example, this is not exactly zeolite, but this is a mineral with very nice zeolitic properties. This is a pentagonite. This is a calcium vanadium silicate. And its dehydration behavior was recently studied by Danisi and Thomas Armbruster and co-authors. And so they found three phase transitions. So the first phase transition occurs in between 296 Kelvin and 373 Kelvin. So here, the hydration state changes from 4 to 3. So there were 4 water molecules per formula unit. Now it's 3. So the space group doesn't change. So the topology of the structure, topology of the framework doesn't change. And then at some temperature, the hydration state changes from 3 to 1, and you see that the framework somehow shrinks. So it changes its conformation state, and then complete dehydration occurs at sometimes at about 470 K. So, and these are unit cell parameters, and we can now apply these complexity parameters to see how the complexity of information behaves in this temperature. So these are complexity parameters. So you see that dehydration doesn't always result in the decrease of information, or decrease of complexity. So for example, this high temperature structure at 448 kelvins is much more complex than this, for example, than these low temperature structures. So the complexity goes like this. So with dehydration, it's always not easy to say how the complexity or how the entropy entropy would behave with increasing temperature. And now another interesting question: how does complexity of zeolites behave in geological systems or in geochemical environments? So there were some field observations in Yellowstone National Park, and so these are shown here. There were some observations that some zeolites form at low temperature, some zeolites forms at high temperature. But to get a more general picture, so these authors, Chipper and Epps, they measured chemical compositions of all these zeolites, and they constructed a phase diagrams to show how different zeolite paragenesis would behave with increasing temperature. So, for example, here you see that these are 4 phase diagrams for different temperatures for zeolites which occur in hydrothermal deposits in silicic volcanic rocks. And so they took into account this analsam, shabazite, clinitolite, so quite a number of different zeolites. So we can now look at the topological complexity of all these zeolites. So here in the respective fields written are the types of frameworks which occur in particular zeolites. And this is topological parameters, topological complexity parameters of these frameworks. And in order to calculate the average complexity of particular section of phase diagram, we can apply what we would call average topological complexity. So we take a specific area of some particular phase in the diagram, normalized to 1, and then we multiply this by the complexity of some particular phase, expressed in bits. So we can use either bits per atom or bits per unit cell, and then we can calculate complexities for different temperatures. So it's interesting that the complexity in this case, with increasing temperature, the complexity of phases which occur in these particular geochemical environments is decreasing. So both in terms of information per atom and in terms of information per unit cell. And I would say also that diversity of the phase diagrams is also decreasing. So it's not only complexity which is decreasing, but also diversity. And what is also interesting that this evolution of the complexity is almost linear, and I don't have any explanations for this kind of linear behavior. So another example is these diagrams for zeolites which occur in VAX and cavities in mafic volcanic rocks. And again, so in this case, these authors, they calculated diagrams for two different temperatures. These are 35 degrees and 100 degrees Celsius. And we can again use this idea to calculate the average structural complexity for these sections of phase diagrams, and we again have a decrease of complexity and decrease of information with increasing temperature. So increasing temperature results in the decrease of both mineral diversity and also complexity in natural zeolite associations. So actually I'm coming to conclusions, and the first conclusion is that structural and topological complexity of zeolites can be estimated using these Shannon information-based measures. So you can have a numerical value which would characterize complexity of either particular topology or particular crystal structure. Then the structural complexity expressed as a Shannon information represents a negative contribution to entropy. And zeolites are actually one of the most complex inorganic compounds and minerals known so far. And with the increase of temperature, structural complexity of zeolites is decreasing if there is no dehydration. Dehydration sometimes results in the increase of structural complexity due to the deformation of the frameworks, which may drastically change its symmetry. And so the last conclusion is that the increase in temperature results in the decrease of diversity and complexity. So the temperature actually kills diversity and complexity. Of course, it was kind of known fact, but it's always good to have this expressed in numerical terms. And we demonstrated this at least for zeolite paragenesis, but I think that for other mineral associations it will be the same. So finally, thank you very much for your attention.
So thinking about it, I've not come down very quickly. So any questions for Sergey? I think this lady's hand was up first.
I have a question with regards to entropy. This is something that we can see with experimental tools. when we have a cluster region in a mineral where you have, for instance, manganese going, you can say this is +3, but then there is electron transfer, charge transfer. This is something that is not taken into account in your model, well, at least not the slide you show. And the question is, how can you make this compatible with the tools we have experimentally to take that into consideration? That actually can make other minerals more complex than zeolites themselves. So the order of complexity will change then.
Yeah, you actually can apply this usual mixing entropy. Excessive. I mean, which kind of tools are you using?
Well, we have many. No, I don't know which ones you use as a reference, but I'm just thinking in terms of the entropy. You must have a data set where you get the entropy from. And for sure, electron hoping will change the entropy values and will not be steady. You will have non-steady state conditions, very fast changes, and so forth. So how can you tackle that with your model?
Yeah, I think if you would know the concentrations of manganese 2+ and manganese 3+, you can apply this mixing entropy approach, which is a kind of textbooks, and then calculate this mixing entropy. So I think, but if you have some dynamic effects, yeah, dynamic switching in your structure, you should. This means disorder. This means disorder, and disorder means that you this disorder means that your complexity would be decreasing. So disorder means less information. So disorder. So the complexity means order. Simplicity means disorder. Yeah. So I think you can apply this mixing entropy in this case.
Thank you. You've clearly shown us how structural complexity is extremely complex, and you've received on a lot of work on quantifying that. Would you agree that if you, thinking of complexity as a whole, that if you think also of compositional complexity, then some of the zeolite group minerals that are solid solutions, really quite complex solid solutions involving not just the cations, extra framework cations, but the framework itself, that would then perhaps be a different angle on the complexity, which won't necessarily tie in with your structural complexity order.
Yeah.
Would you agree?
Yes, yeah, absolutely right. So you can calculate chemical complexity if you know chemical composition just using this Shannon information formula. So you can calculate this Shannon information which is contained in your formula by just considering these coefficients as a numbers. So then you sum them up, and then you use these probabilities to calculate this using Shannon formula. Actually, it was done in the 70s by some by some Soviet at the time Russian scientists, some of my older colleagues, and so they calculated geochemical complexity. What they say for different types of rocks, for Moon, for example, for the Earth, and all. But I think that it will be interesting to look at this again. So.
I think the gentleman here was next.
If you consider the fork system, for example, there are zeolites having 3-dimensional fork systems, and there are zeolites 2-dimensional fork systems.
Yes.
1-dimensional.
Yeah. I would transform your question into a more general one. Does density of zeolites somehow relates to their complexity? No. So we check that the framework density doesn't have any relation to structural complexity, and also, of course, if density doesn't have any relation, then probably the dimensionality of this channel system also doesn't have relation.
Which way you look at it, or in which plane? For example, if you look in 1-dimensional system, it's very simple.
It's an interesting idea. Yeah, maybe we have to look into this in more details. Yeah, thank you. Yes.
I wonder whether there is a link to the statistical process of nucleating such phases. Is there some kind of linkage between the entropy of your structure, the complex structure, and nucleating this phase?
Look at
Nucleating.
nucleation. Oh, this is also interesting. In 1956, Julian Goldsmith from the University of Chicago published a book, not a book, a paper about simplicity, something like simplicity of crystals, where he pointed out that if you have metastable crystallization, then their crystals, polymorphs with a smaller unit cells, with a lesser complexity, would crystallize more easily, because the nuclei, the critical nuclear, the size of critical nuclei would be smaller. So if you are in some kind of metastable region of crystallization, so for example, this protodolomite, yeah, this is which is disordered phase, which crystallizes under metastable conditions, and then which with years and age, it transforms into a stable polymorph. So, of course, there is a direct correlation between the complexity of crystal structure and the size of critical nuclear, which is needed for the phase to start crystallize.
Well, in most nucleation models, this is handled by the interface tension, which is then for the metastable phase is usually smaller than for the stable one. But maybe this is not the only parameter.
Yes, this is not the only. Yes, this is not the only parameter.
For example, in reservoir rocks in the North Sea, for example, the pore fluid is heavily supersaturated towards illite, but illite doesn't nucleate. So there must be something else besides a simple difference.
No, of course, complexity is not the only parameter. I mean, this is just one of the parameters which control the crystallization and occurrence of some particular phases, yes. This is only part of the picture, of course.
We have another question right to the back. You could speak loudly.
Thank you for a beautiful presentation.
Thank you.
From University of Latvia. It's a tricky, curious question about amorphous crystals and radioactive who are falling apart. How do you calculate? Is it possible?
Well, this is always a question which people ask me, how this, what is more complex, piece of glass or piece of quartz? Which one is more complex? And so one of my friends, he says, well, a piece of glass is much more complex because of their disorder. But if you look at the complexity in terms of the number of microstates which realize the given macrostate, then the piece of quartz would be more complex than the piece of glass. But to be honest, I'm not sure how to answer this question about amorphous state, because this idea was applied for crystals, so it was actually designed for crystals. So maybe for amorphous states, because you also need to take into account this short-range parameter, short-range interactions, which are in glass, they are present. So actually, I don't know. But if you look at this from this viewpoint of this Shannon formation theory, then the complexity of piece of glass would be zero, because there is no crystallinity. But this doesn't mean that it is really zero.
About these radioactive minerals which are changing in time as well?
This is an interesting question. Yes, we also looked at this. So one of my PhD students from China, she did. She heated one of these metamect minerals, and then we looked at different temperatures, and we looked at the structures with the crystalline compounds which were formed, and then looked how the complexity is developing. The complexity is actually increasing because this amorphous state is a kind of metastable state. So if you apply energy and begin to crystallize, so it begin to kind of order in the system increases, and then complexity is also increases.
Any further questions? If not, I suggest we thank Professor Krivovichev again.
Thank you once again for this honor. It's a great pleasure.